Hey everyone, welcome. Today we're going to dive into a really fundamental shift in how AI language models actually, think. It's a brand new approach that's designed to smash through a major bottleneck, the one that makes AI so slow and expensive. The goal? To teach it to think not in single words, but in entire concepts.
It's a question you've probably asked yourself, right? We have these incredible AIs that can write code, create poetry, whip up amazing essays, but they come with this huge computational price tag. Training them, even just running them, takes a massive amount of resources. And that makes them super expensive and really limits who can get their hands on them. So what is actually going on under the hood that's causing all this? Okay, let's get right into it. The root of this whole problem is buried in the very foundation of how these models generate text. For all their incredible power, they're basically building a masterpiece one tiny grain of sand at a time. It's a process that's just incredibly repetitive and, frankly, super inefficient.
And that little grain of sand? It's called a token. You can think of it as the AI's version of a word, or sometimes even just part of a word, like a syllable. Every single sentence, every paragraph, everything an AI writes is built by predicting these tokens one after another, in this long, painstaking chain.
And here's the kicker, the really wild part. Each one of those steps accomplishes very, very little. A single token, which the model has to pick out from a vocabulary of over 32,000 options, carries only about 15 bits of information. That's tiny. So the AI is doing this monumental amount of work just to predict the next little, low-information piece of the puzzle.
This isn't the first time we've hit a wall like this. The earliest models worked character by character, which was just painfully slow. Moving to subword tokens was a massive leap forward, a huge win, because each prediction suddenly carried a lot more meaning. But now, it feels like we've squeezed all the juice out of that approach. To get to the next level of efficiency, we need a completely new idea.
And that new idea is, what if we just stop thinking in discrete tokens altogether? This is where a method called CALM comes in. It stands for Continuous Autoregressive Language Models, and the core idea here is to completely change the AI's job. Instead of choosing the next token from a list, it has to predict the next vector, which is this rich, multidimensional representation of a whole chunk of text.
So how does this magic work? Well, it's actually a pretty elegant four-step process. First, CALM grabs a chunk of tokens, say 3 or 4 words, and groups them together. Then, it uses something called an autoencoder. You can literally think of it like a zip file for language, to compress that entire chunk into a single, dense vector. Now the language model's new job is just to predict the next vector. And finally, that predicted vector gets decoded or unzipped back into the original group of words. And this is where that huge efficiency gain comes from. See, a normal model takes, let's say, T steps to generate T tokens. But by grouping 4 tokens into one vector, CALM can generate the exact same amount of text in a quarter of the steps. It's that simple. Fewer steps means less computation, which directly leads to a faster and cheaper model.
But of course, a brilliant leap like this creates a massive new problem. The old models worked because they were just calculating probabilities over a finite list of tokens. But the space of possible vectors? It's infinite. You can't just pick one from a list, and that means all the standard tools we use for training and evaluating these models are now completely and utterly broken in this new continuous world.
So to solve this, the researchers had to go back to the drawing board. They had to build a completely new set of tools from the ground up, a likelihood-free toolkit, as they call it, designed specifically to work in this strange new world of continuous space. Which, of course, leads to the million-dollar question, doesn't it? If you can't calculate the probability of any specific outcome, because there are infinite outcomes, how on earth do you teach the model what a good prediction even looks like? And how do you score its performance?
The full toolkit has 4 main parts. You've got a really robust autoencoder. That's what creates the vector space. Then there's a new method for training the model without probabilities. There's also a new way to evaluate it. And finally, you get a new technique for controlling the model's creativity. The job that's usually handled by something called temperature sampling.
Let's just zoom in on one of these for a second. BrierLM. This is so cool. Think of it as a brand new report card for AIs. Since it can't calculate exact probabilities, it instead evaluates the model by asking it for a bunch of samples of what it thinks the next vector should be, and then it compares them. And what's just amazing is that this new metric shows a nearly perfect correlation with the traditional metrics, so we know it's a super reliable way to measure performance. So,
Okay, we've got the theory, we've got the fancy new toolkit, but does it actually work? Does it pay off in the real world? Well, this is where we see the results. And they really do demonstrate a powerful new way to scale AI. It's about making each step more meaningful, not just making the models bigger and bigger.
All right, just take a look at this table. If we compare the standard Transformer S model to the new CalM model, you see something really fascinating. Now, the CalM model is actually a bit larger. It has more parameters, but look at the training flops, which is just a measure of how much work it took to train. The CalM model achieves a better score with way less computational work. That is the efficiency payoff, right there in black and white.
And this chart just hammers that point home. To get to the same level of performance, the CalM model needed 44% less computational work during its training. I mean, that is a massive improvement in efficiency. And it's all because they fundamentally changed the task itself. And really, the authors of the paper put it perfectly themselves. They said this is about scaling the information capacity of each step as a powerful new lever for computational efficiency. So instead of just throwing more data or more parameters at the problem, we now have this brand new lever we can pull, just increasing the amount of information, the pure meaning, packed into every single step the model takes.
And that really leaves us with a fascinating final thought, doesn't it? This research shows the incredible power of taking just 4 token steps. But where does this road lead? What new abilities, what new efficiencies are going to be unlocked when an AI can reason and generate text, not just in words, but in entire sentences, or even paragraphs, or maybe even whole ideas at a time?